Okay, I think I think it's already time to start. Recording as in progress. Okay. All right. So actually, in the previous lecture, we started discussing Riemannian manifolds. So let me remind that, right? M pair MG is called a Riemannian manifold where G is a Riemannian metric on M, which means that G is a positive definite. So I will be writing it here with indices. So the sum by ij, gij of x, dxi, tensor product dxj, and my matrix gij is symmetric for all ij, and the matrix gij x is positive definite, right? So we kind of think of matrices that live in tangent bundle, and I can say that actually this is a matrix whose entries smoothly depend on, so it is a smooth, right? So it is a smooth tensor to field. And my matrices are positive definite. Okay. We discussed some examples, and one can take Rn or any open. In fact, you can take any open U in Rn and equip it with the standard Euclidean metric, which I denote by GE, which is just a matrix where this matrix is identity in every, in every point, right? So in this sense, my matrix looks like that. It is dx1 squared plus and so on dxn squared. And we started discussing another example. The second example was the upper half plane model. So I am writing it here. Upper half plane U2 equipped with the metric which I denote by GU. And this metric is, so U2 is my x, y, such that y is strictly positive, right? Or one can think of complex numbers such that the imaginary part of z is also strictly greater than 0. And I will take the metric, which in this coordinates looks like GE over y squared. So it's Euclidean metric, but scaled. So one can, like, in the sense of tensors, one can write as dx dx plus dy dy over y squared, right? Okay. We also were discussing geodesics, and I want to discuss this like geodesics in the upper half plane model in a bit more detail. So the idea is that before moving to geodesics, let me also remind that I defined isometries, right, of Riemannian. You remember what are isometries of Riemannian manifolds? Yeah, it's one of the, indeed, it's one of the examples. Let me define it more generally again. So F between M, G, and another Riemannian manifold N with the metric H is called an isometry, if the, okay, so let me make a comment here. G, right, like a remark. So G actually, it kind of sits in, so we have a manifold, right? And we have a pair of tangent vectors. So G applies to a pair of vectors where my vectors U and V belong to the tangent space TPM, right? So this is my tangent space TPM. How to get this tangent space? You can consider one takes all possible smooth curves passing through this point. So imagine I have a curve, right? This is my curve gamma, and this is the image of some segment, say, I don't know, AB or 0, 1, doesn't matter. So I have a smooth map from the real line to my Riemannian manifold, right? I discussed the details on the last lecture, so we will, it is like, you can try to recover some details, but the idea is that you have a smooth map here, you can always compute. So suppose this point P is, I don't know, assume that these are all 0, right? So AB contains 0, and assume that P is just gamma of 0. And then tangent vector here is just the velocity vector gamma prime of T. It is an element of this tangent space. The only point that we, like, the important thing is that we need to take, so let me write down this somewhere here. So TPM is the set of equivalence classes of gamma prime of T for all gamma passing through P, right? So such that gamma of 0 is P. So this is my tangent space, okay? My tangent space at the point P is the set of equivalence classes of velocity vectors. So the derivatives, yeah. Gamma, yes, here it should be 0 indeed. Yeah, thanks. It is 0. So indeed we take gamma prime of 0. Since I'm fixing the point, right? I'm fixing the parameter. So I'm taking all the gamma passing through P at the 0 point. So yeah, and okay, we apply the Riemannian metric to the pair, right? In fact, how do we apply? We see here those dxi, dxj. We can think of them as linear functions sitting in the dual vector space, dual to that one. And thus, I have curves that are images of just standard coordinate lines in my local chart, right? Again, remember we are talking about smooth manifolds, which is glued from many charts. So we kind of have this local, we kind of study local behavior at every point. And yeah, and then dxi applying to my basis. I can choose the basis, which is the tangent, which consists of tangent vectors to my coordinate lines, right? I have always those local coordinates, x1 and so on, xn. and there dxi applied to the jth vector is the Kronecker symbol, which is 1 only if I equals j, right? So applying, you can write down your tangent vector. Any tangent vector can be written in coordinates, right? It will be just a linear combination of your basic vectors. And then you plug in this here and you obtain, so like generally it will look, yeah, I don't know, like want to write it, but like it will generally it looks like that, right? You have here some, I don't know, G sum of lambda I ui, right? And sigma mu j vj, right? Well, actually also, let me write them this way. EI is my basis, right? So I have sum by I, sum by j, and then I can use linearity at every fixed point. Okay, so this map is an isometry if the differential of f, and remember, yeah, so again, this picture, it is known that if it is P, then this is F, this is another manifold N, M, and here is my TPM, and here is the tangent space T, F of P, N, and it is known that the differential is just a linear map, right? So the differential maps tangent vectors from this tangent space to tangent vectors to this manifold. So if I'm taking df, I should actually write like p, that the differential is computed in p, that for every pair of vectors there, let me, okay, so I have vectors here and some vectors here, right? Okay, so I think I will, so H, right, applied to the pair dpf-u, dpf-v is equal to G. This form is at the point P. This form is actually computed at the point f of P, right? And this is just U and V. So in this picture, right, I have tangent vectors UV. They are mapped to dfu and dfv, correct? So you apply the Riemannian metric, which lives here. You apply it to this pair of vectors, and this is the same as applying this Riemannian metric, this bilinear form, to this pair of vectors here. Yeah, so they should agree. Well, and of course, I didn't write also that f. So we have 2 bullet points, and f is a diffeomorphism. F is a diffeomorphism, which is very important. My manifolds are even better. They are homomorphic, but even stronger. We have a diffeomorphism. And okay, so there is an important theorem that in particular, if gamma, okay, let me even write it. So if f is an isometry and gamma is a smooth path, right, smooth curve in M, then f of gamma is certainly a smooth is a smooth curve in f of m, and the length of gamma on every segment AB is the same. So, like generally speaking, if I have an isometry, right, I have an isometry between M and N with matrix G and H, then this length is computed with respect to the metric G, right? And this metric here is computed with respect to H. So this is the length of the curve f of gamma, restricted also on AB. And yeah, and the formula for those lengths are, yeah, so the length of gamma restricted on, well, I usually omit the t belongs to A of B, right? This is the integral from A to B. If I want to specify the metric, I'm using sub G notation, right? And this is computed as the same way we compute the length of the curve in the Euclidean spaces. And this is just the square root of G. Yeah, so I need to, how is it computed in Rn or in R2? You take the square root of, and here you usually write gamma 1 prime squared plus gamma 2 prime squared and so on. This is because you just use here the Euclidean metric. So let me rewrite it in the, like, our Riemannian metric notations. This will be gamma prime of t, right? It's scalar product since the norm of any tangent vector, right? So important thing that the norm of any tangent vector, then, since now we live in some abstract manifold, so the feature of this Riemannian geometry language is that we still can compute norms, we still can compute lengths and so on. So the norm here is just the square root of G of U, right? So our U times U, the scalar product of U with U, it should be just done with respect to this Gram matrix G. Again, since vector U is actually, it is a tangent vector with some fixed point P, then it is like, you kind of imagine, well, it is not necessarily like to write it all the way, but you keep in mind that the point is fixed, right? The point is fixed. But nevertheless, you can move along curve. That's why you change the tangent space, right? Your tangent space also changes. And how it changes? How does it change? It changes along the curve. So the point here is gamma of t, right? So it is just my curve from gamma of A to gamma of B, and all intermediate points are gamma of t. And I need to compute the velocity, the norm of the velocity vector at every point here. So my norm varies, it's a function with respect to t, and I integrate it over the interval A to B, okay? So this gives me an opportunity to define geodesics and actually define the distance. So the distance, or I usually denote it by rho, right? So the distance between any two points P and Q is, by definition, the infimum of lengths of curves gamma, such that, again, so it's restricted on the segment 0, 1, such that gamma of 0 is P, gamma of 1 is Q. So I'm computing all the lengths of curves connecting P and Q. And I always can choose a parameterization such that gamma of 0 is P and gamma of 1 is Q, right? And so I compute many such lengths, and the one which realizes the distance is called a geodesic. So gamma is a geodesic, right? If its length on 0, 1 precisely equals the distance between 2 points. Again, this is important that geodesics do not always exist, right? Since, I mean, infimum exists, but not necessarily you have a line whose length, right? You do not necessarily have a curve whose length really realizes the distance. So this theorem, right here, it says that the length of curve is preserved under any Riemannian isometry. So in particular, if I consider an isometry from M to itself, I also map like curve of length L to another curve of length L. And in particular, as a corollary, I also, it is a like very nice, it is a diffeomorphism. So I can always also go back. So it maps geodesics to geodesics, right? So the corollary F maps geodesics to geodesics. And we applied this to the upper half plane. So let me remind that the upper half plane, right? So now let's get back to this example. I want to discuss this example a little bit more, and then I will say a few words about homogeneous spaces, since we will see how to view H2 as a homogeneous space. Okay, so in this example, right, we have a half plane U2 with its non-Euclidean metric. By the way, right, a remark, you can equip the same U2, you can equip just the Euclidean metric, and their geodesics are well known, there are straight lines, right, in all different directions. Okay, now here, I'm going to show that actually either vertical lines or circles orthogonal to the boundary are geodesics. So the claim, geodesics are either vertical lines or circles orthogonal to the line y is equal to 0, right? So this is our claim. And the idea of the proof, right? So the proof, yeah, okay, good. So the proof of this claim is based on the following steps. We first note that the automorphism group of U2, which is which consists of maps Z to AZ plus B to CZ plus D, where A, B, C, D are real, such that AD minus BC. Okay, since this map is the same, I can just write that this is equal to identity, right? And which is isomorphic to, it is isomorphic to the group PSL to R, right? We discussed that you can think of this as a matrix A, B, C, D, and the condition that AD minus BC is equal to 1 is precisely the condition that the determinant is equal to 1. This gives us the following group. Okay, so the first claim is that actually this group acts as an isometry group. So it is sitting in the isometry group of U2. Well, I will write with a pair like with this metric, but from now on I will omit this notation, right? I will usually just write H2 or U2. Okay, so this is an isometry subgroup. Why? Since you can decompose any fractional linear transformation or a Möbius transformation in the decomposition of 4 elementary ones, and for every, you can show that this will preserve this metric. But for this actually example, we do not really need even the whole group. We just need to find one transformation. So suppose I have 2 endpoints. So say like B. Okay, my points are some P and Q, right? And I have alpha and beta as endpoints. So as a special case, right, in particular, I think I will write this way. In particular, in isometry, okay, for an isometry F of Z, which will be denoted by, it is, okay, sorry, it will be defined by Z minus alpha over Z minus beta. It sends, how should I denote this? Okay, let me denote this circle by, okay, omega, and this one by gamma. So the claim is that it sends omega to gamma. Indeed, I can check that f of alpha, it is just 0, right? F of beta is just the infinity point, right? And then use that f is also a decomposition. It is also a decomposition of an inversion, as we discussed last time, and translation, I guess, right? It is translation and inversion. Okay, yeah. Just recall that elementary guys are z to I don't know, z plus alpha, also z to, you can multiply it by any number with absolute value 1 and apply shifts. So it is a rotation, translation. Also, I can have dilations where lambda is positive, right? By the way, alpha here is real. It is important. And lambda here is definitely also real, as I write, it is positive number. And so type 1, type 2, type 3, and type 4 is z to minus 1 over z, right? I made a typo somewhere, and it's it was noted that it should be minus 1 over z, since it interchanged, it should preserve the upper half plane, and it interchanged 0 and infinity. What is interesting about the other types, for example, this dilation, it sends 0 to 0 and infinity to infinity. So it fixes, it lives invariant, this geodesic. And by modifying this f, using this, right, by composing f with this dilation, I can actually arrange the image of P and Q to be my favorite points. And I guess my favorite point is I, and I think some, I don't know, AI, right? So I think that I can do it actually. I cannot control A, since it depends on the length of curve omega from P to Q, right? But I can control where I send the first point. And actually then the second point will be either here or here. And in this fact, actually, I also can control by maybe inverting. But, oh, I really do not need it. In fact, I really do not need it, even this. It's just convenient. One can send it to any AI and BI, for example. It's not a big deal. Okay, so remember, okay, again, what is my steps, right? The second claim is that for any 2 points sitting on the vertical line, and let it be, as I said, it doesn't matter. I can choose one of them to be I, but we are actually good. Let it be just AI and BI. So the second claim is that for those 2 points, geodesics, so geodesic joining AI and BI is precisely the vertical axis. So it is the line x is equal to 0, right? This is the second claim. So once I prove this, I get everything, since we use the isometry effect, right? We use an isometry machinery. And yes, and we use effect from complex analysis that this group acts transitively, right? This group acts transitively on upper half plane. So this is the group of conformal, so this is the group of conformal automorphisms of U2 acts transitively, which means that you can send any point to any other point. Okay, all right, that's good. So we can try to write it down somewhere. Probably let me do it here. And I think I should move. Yeah, the camera to the left side. Okay. So remind that the metric was so we proved the claim about a vertical geodesic. So GU is, what is it? It is GE over y squared, right? My gamma of t is gamma 1 of t, gamma 2 of t. And the length with respect to this metric GU of gamma is, what is it? It is the integral from, I should choose somehow the point. Okay, let it be just from 0 to 1 for a while, okay? So it is, how does it look like? It should be square root of gamma 1 prime of t squared plus gamma 2 prime of t squared. over, I think, gamma 2 t dt, right? And my gamma looks like gamma of 0 is the point AI. Gamma of 1 is the point BI, right? Correct? So I am saying that gamma 1 prime squared, what's going on with this guy? It is always positive, or, well, the least value is 0. So using that, gamma 1 prime of t squared is always greater or equal than 0. I'm writing that this is greater or equal to the integral from 0 to 1. And what do I obtain here? Wait, is it? I think it should be gamma 2 squared, right? It should be gamma 2 squared. So since I'm dividing by y squared, yeah, so I forgot to. It's actually important. Otherwise, I would get something different. So here we get gamma 2 over gamma 2 squared dt. Reminds 1 over gamma 2, right? Yeah, but gamma.
Or you should put the whole thing inside the square root.
Yeah, but we are sitting in the upper half plane, so I guess that gamma 2. We know that gamma 2 of t is positive, right?
Sure.
Or, yeah?
Yeah.
I think I can use it, yeah. So, in fact, it's just 1 over gamma 2 t dt from 0 to 1. And
So then you don't need the square. But then you don't need the square.
Yeah, in fact, where?
The denominator, so.
No, oh, sorry, it should be, yeah, something is weird.
So the whole thing, either the whole thing.
It should be gamma 2 prime, yeah. Anyway, I'm doing just some, let me think. So gamma 2t is positive, but it doesn't mean that gamma 2 prime t, right? Yeah, so yes.
My comment is that the denominator, you don't need the square.
Here?
Because that shouldn't have the square. Because, yeah, because that, the whole expression should be under the square root. Right?
Yeah, the whole expression, right? The whole expression, indeed. So yes, correct. I do not need the square here because the whole expression was under the root. Yep, exactly. Since it is the integral from 0 to 1 of the square root of, yeah, g gamma prime, indeed. Okay, yeah, so it was the whole square. So kind of here is absolute value, but we don't need absolute value because of that, right? And eventually we get this. Okay, this is, this should remind us the logarithm actually. So, well, I can just plug in it here. And this gives me what? It gives me the log of gamma 2 of t, right? From 0 to 1. Yeah. And since I know that this is AI, okay, this is a little bit weird. I kind of, no, it's okay, actually. Yeah, log AI minus log BI, which is just, sorry, I need to actually write BI minus AI, right? Because of gamma of 1 is this. Yeah, but we will then kill i's, no?
Yeah, so that we're using the identification of R2 with C.
Yes.
Yes.
Yeah, okay, I agree. Yes, you're right. I kind of plugged in gamma, not gamma 2. Yeah. But the point is that gamma 2 of 1, it is B, and gamma 2 of 0 is A, right? So indeed, you're totally right. I cannot get here actually anything complex. I need to get anything. I need to get something real. So this is this ratio. And this thing, right? This inequality, it becomes inequality if and only if and only if what? If and only if gamma 2 is sorry, if and only if gamma 1, yes, gamma 1 prime 0 is identically 0. But this means that gamma 1 itself is a constant, right? In this particular case, we know what the constant is. Yeah, it should be 0. Okay, is it good? Yeah. So now let me switch for a little bit to the right board again. Yeah, the idea we take if our points are already on the belonging to the vertical line, we just use this argument. If our points are not from the same vertical line, then you can always find a circle, right? You can always find a circle passing through P and Q such that the circle omega is orthogonal to the bound, which means that the center is here, right? You can always construct it. It is I can say that I could say it's kind of like a high school geometry exercise, actually. Very nice, yeah. And then you find an isometry with respect to this model, which sends it to a vertical line, and then you again apply this argument. So our geodesics are not straight lines, but our geodesics in this model, in this upper half plane model, are vertical lines, and the circles are orthogonal to the boundary. What is interesting is that, right, I wrote it in the end of the previous lecture, that this automorphism group, right, I said that it is a subgroup of the isometry group of U2, but in fact, it coincides with the orientation preserving isometries. This fact is already a little bit more complicated. So to see that it is just an isometry subgroup, it's not that hard, but to see that it coincides with the isometry group, it requires a little bit more steps. But what one can think of, in fact, I usually prefer to prove it using another model. And it is interesting that having different models of hyperbolic space is very useful. In particular, we will discuss, I think, probably not today. I wanted, well, but actually maybe we will start. Yeah, maybe we'll start a few models today. So the idea is that what does it mean having different models? It basically means that you have a Riemannian isometry between one model and another, right? With Euclidean space, you can actually also find some other models. So probably you can find the diffeomorphism sending R2 to the open disk, but then it's just not so convenient. So we just basically with R2, it's kind of an exceptional thing. You will usually make it less convenient if you send it anywhere else. However, with a hyperbolic plane, So so this is our geometry, points and such geodesic lines. So for example, in the hyperbolic plane, in the upper half plane, there is this triangle having 3 zero angles, and there is another triangle, right? And an interesting fact is that actually the automorphism group acts transitively on triples of points, including the points from the boundary. And if you want to send this triangle to this triangle, there is an isometry doing that. And one of the isometries which can arrange this mapping is just that isometry -1 over z, well, maybe shifted depending, but if it is 0, if this point is 0, right? So just before the break, we will do a 10-minute break, but what does z to -1 over z? It takes, let me use another color. So we take, and here is the point 0, right? So we take this triangle, the green one, to the blue one. So it sends green triangle to the blue triangle. And this is an isometry. And in fact, any triples, any ideal triangles, so-called ideal triangles, are isometric to each other. But there is an exercise, you can find another isometry also doing the same. So you can kind of rotate angles, you can rotate triangles, you can reflect with respect to the circle, or you can do something else. You can also rotate probably around I think you can rotate it around this point, so you can do central symmetry, right? So there are different ways. Anyway, so let's do a 10-minute break. Yeah, let's make a 10-minute break, and then we will discuss other isometries, and maybe I will mention Lie groups and symmetric spaces. Okay. Okay, so we continue, and I wanted to discuss the following. I wanted to talk a little bit about isometries of the plane. So let us write this proposition. So let okay, how should I denote it? Let z be any point from U2, right? And let G be this isometry subgroup, which is the Möbius group of U2 or the morphism group of U2, anyway, the group of conformal automorphisms. And I will say that it is PSL to R, right? So why is it PSL to R? Since it's the quotient. So this is the quotient of SL to R by plus minus identity. This is precisely the kernel. So again, I'm writing this down. It's not very nice, but this is how it is. This is the kernel of the map phi, right? That sends any isometry of this form to the matrix ABCD. Yeah.
ABCD.
Oh yeah. Wait. You can take any ABCD.
Yeah. But some of them give you the same.
Yes, and some of them. Yeah, and that's why they sit in the kernel. No.
they differ by
plus minus identity.
also like the, yeah, so the kernel should be in the domain, right?
Yes.
So the kernel should be in the group of matrices.
Ah, okay, you're right. Yeah. Yes. So this is my phi from the set of matrices ABCD to this. Yeah, the isometry is the same, while matrices are algebraically different. Okay, so what I want to prove in this proposition, I want to prove that the stabilizer with respect to G of any point Z, so the stabilizer, it is also sometimes just written as stabilizer, sorry, of Z. I want to show that this is the special orthogonal group, right? And how I'm going to prove it? First, I want to say that since my group acts transitively, it doesn't really matter which point I choose. So without loss of generality, I can choose, I can pick Z to be, again, my favorite point inside the upper half plane model is I. So we are picking this. And now we just write down that GZ, it consists of all points, right, that preserve. So these are all elements that preserve my point Z, which stabilize this point. And so I need those A, B, C, D such that AI plus B over CI plus D is I, right? This implies, well, what does it imply? This implies that AI plus B is equal to DI minus C. I just multiplied this, the denominator on the I, and this is equivalent to A being equal to D and B being equal to minus C. That is, my matrices are, so then G I, right, it is isomorphic to the group of following matrices A, B, minus B, A, such that the determinant is still equal to 1. But the determinant now is A squared minus, which is plus B squared is equal to 1. And this is a famous interpretation of the special orthogonal group. So this is isomorphic to SO2, where I can write that SO2 consists, right, by definition, it consists of all matrices A such that A transpose A equals the identity and the determinant is equal to plus 1, right? Again, if you like do not remember the details, just write down that this is 2 times 2 matrix and simply write this condition and you will get the same description. This is an interesting observation. So the claim is proved. I mean this proposition. And an interesting fact is that we have for any point we have the same stabilizer. Yeah.
We can choose setting sign. Is it because it acts transitively?
Yes. Yeah. Because let me write it. Since there is an isometry F from G, right, such that G of Z is I, right? Basically because of that. And okay, this kind of thing, this kind of means that there is some, okay, I can think of points in my upper half plane, and I can kind of assign to every point this stabilizer, right? So there is this, okay, so interpretation. Let me. There is this correspondence between Z and the stabilizers, which are all isometric. How to make this correspondence more explicit? Consider this map, which stands Z to some element. Okay, I choose a base point, right? I choose a base point. And for every Z, right, there is an isometry such that GI is Z, correct? So okay, for every Z, right, there exists G such that GI is Z. I now prefer to use the like standard group notations. Okay, now my Z corresponds to G multiplied by, let me, since it is the so-called compact Lie group, right? We will just get to Lie groups. Yeah, this is the idea. So I'm considering this map. I assign to each Z the corresponding G. But I do it not just like G. I want to assign, since there are many, the point is that mapping here, okay, let me make it more. So the idea is that I kind of fix the disk around I, and I fix the disk around Z. And in fact, this isometry sends disk to the disk. But there are many such isometries. The idea I'm trying to sell you right now is that I can take just some simple isometry and then rotate around this point, right? And back. I can send it back and then rotate around this point. The point is that these points are, I want to make a one-to-one correspondence, and that's why I need to multiply it by k, right? I want to multiply it by k. So there is a one-to-one correspondence between the points sitting in my U2 and the elements that look like G times K. G times K is actually an element of the quotient G mod K, where I'm thinking about the orbits, right? Basically, I'm thinking about the equivalence classes. So I have two elements where, right, where G and H, okay, it's not a good, okay, I will write it this way, right, where H belongs to GK if, what should I have? I should have that H, the G inverse H belongs to K, right? And this is precisely what I just said geometrically, that while sending this disk to this disk, so there is one-to-one correspondence between, say, unit disks surrounding I and Z. But there are many isometries sending one disk to another. In order to like eliminate this many isometries into one class, I take the quotient by this same compact subgroup fixing I or fixing Z. Yeah, that's the idea. And this roughly, so thus we like roughly proved, but like very roughly, that U2 coincides with the quotient G mod K, where G is PSL to R and K is SO to R, right? That's the idea. And in fact, this leads us to the discussion of homogeneous spaces and Lie groups. Yeah, we will actually, we are going to use it a little bit in this course. So I'm going to explore this a little bit more. So this is a homogeneous I forgot its the correct spelling. Homogeneous, is it correct? What this is? Okay, homogeneous space. Homogeneous precisely means what I just said. The neighborhoods are isometric, and there is this one-to-one correspondence. That's why it's homogeneous, since indeed the neighborhood of any point is the same everywhere in your hyperbolic upper half-plane model. Okay, now about Lie groups. So should I switch? Yes, I guess I should. Oh, I can just I can just go here. So now the Lie groups. Okay, so by definition, a Lie group is a Lie group is a smooth manifold. Okay, okay, Leah, it is a smooth manifold with two algebraic structures, right? With algebraic, with a group algebraic structure. Group structure. So there's a smooth manifold G. Let me put it here. Yeah, G with a group structure. So we have two operations, right? We have multiplication and okay, such that the product, right, the multiplication and I will denote it by I, the inversion, so G to G. So this goes as G inverse and G1, G2 is mapped to the product. So such that these two maps are smooth maps, right? Are smooth maps. Or in other words, we have a group which is equipped with the structure of a smooth manifold, such that the group operations, right, are smooth with respect to this topology. So these guys are group operations. I just want to highlight not just some maps, right? Definitely we are interested in the, okay. So this is a definition. And there are many examples of Lie groups, and a very classical example. So the first example is definitely GLN, right? GLN. Let us consider right now real Lie groups, but in fact, any complex Lie group can be considered as a real Lie group of just the dimension 2n. So GLN R, right? It is the set of matrices of the squared matrices such that the determinant is not equal to 0. And this set of matrices, it is homeomorphic to Rn squared. So eventually we just get, let me move it up. So we obtain the subset, we'll basically obtain an open subset in Rn squared, right? So GLN of R is an open subset in the space of matrices. And definitely it is a manifold. And why? So why the group operations are smooth? Since you can write down that, right? How do you multiply one matrix onto another? You take the row and take basically the scalar product of a row and the column of your two matrices. It is actually just a polynomial operation with respect to coordinates, with respect to matrix entries, right? So the product, so I write in particular, for example, the product, right, is a polynomial map with respect to entries. Same for inversion. And here, the fact that the determinant is not 0 is very important, since you probably know the formula of the inverted matrix, that you can compute the minors, right? Like they are called algebraic complements, as I remember, of your matrix entry. You kind of kill the row and the column, compute the determinant of the matrix, and you should divide it by the determinant of your initial matrix. Since the determinant is not 0, this means that the inversion, right, taking the element G inverse, it is a rational polynomial map, right? And this again, it is a like very nice smooth map, since the determinant, sorry, the denominator of this rational map is not 0. So this is my, okay, this is my first example. Now the second will be already very close to what we just discussed. The second example is SLN. Oh, I raised it and I didn't make a comment for about this. Yeah, there was some minor issue with the absolute value, but okay. So the second example is the group SLNR, which again is the group of matrices such that the determinant is equal to 1. Again, same idea, but the dimension is already different, since now we have one, this is a set described by one equation, right? So this kind of it is like a set x sitting in Rn squared, right? Such that some f of x1, 1, x n is equal to 1, right? This gives us a kind of something non-degenerate. How to check this? One needs to differentiate df, right? Okay, differentiate f of x is equal to 1. So what do we get? we get that df, well, df is already a linear map. It will consist of so df applied to the point x, so it will be applied to u1 and so on, un squared, right? It is equal to 0. I need to check that this is not degenerate linear map for every x, right? So one needs to differentiate f of x and check, basically check that df is non-degenerate for every x belonging to epsilon r. Here we are going to use one trick quite popular in the theory of Lie groups. Lie group also it is a very nice manifold actually, since you can take any point x, you can multiply it by x inverse, and it gives you a diffeomorphism from the neighborhood of x to the neighborhood of the identity. This roughly means that it doesn't matter, usually doesn't matter like which point you consider, you can pick any convenient point. Definitely for linear groups, convenient point is an identity matrix. So we are taking this differential, and in fact, this is an exercise, but you can indeed, I mean, I did it like several years ago by my own when I was a student. You can just check that the differentiation of the determinant of x in the identity matrix gives you the trace of I will call it dx, right? If x is an element of our group, okay, x is epsilon r, then dx actually already is an element of the tangent space and the identity element of the group G, right? And it turns out that if you then see that this trace it gives you a non-degenerate thing when x is identity. In fact, you will obtain that Ti of G, it consists of all matrices x such that the trace of x is 0, right? This is the this is so-called Lie algebra. And interestingly, you can see the dimension. This implies in particular that the dimension is equal to n squared minus 1. Since the condition that the trace is equal to 0, first of all, it covers only diagonal elements. But if you choose n minus 1 of the n diagonal elements, the last one is already uniquely determined, right? So the condition that the sum of n elements in the diagonal is 0, it is simply it gives simply the like hyperplane in it is a hyperplane in the real vector space of dimension n squared. So this is epsilon r, and for example, we see that when n is equal to 2, right, the dimension is 3. So the dimension of this group is 3. And one can actually consider the group of complex matrices also with determinant 1. Like on the first glance, it gives you a complex Lie group, but any complex Lie group can be considered as real Lie group, since you can think of any complex number as just a pair of real numbers, right? And this gives you, for example, SL. Let me probably write it somewhere. Okay, let me write it here. I would say like remark. So the dimension of SL to R is 3, right? The dimension of SL to C over C is also 3, of course, right? We just chose a basis and we do the same way, but we just work on over complex numbers. But this implies that the dimension of SL to C, but considered over R, is 6, right? This group SL to C also will play an important role in our course. It turns out that this group will be an isometry group of the three-dimensional hyperbolic space. So, and there are different approaches already to three-dimensional space, again, since we have different models. And that's why it is a particularly interesting group. Okay, now I wanted to, I think I have some time. I wanted to mention now the third example, orthogonal group, which is also very important. So orthogonal group ON of R, it consists of all matrices such that A transpose A is the identity, right? So this is the group of matrices preserving standard Euclidean quadratic form. In fact, it is an isometry group of the sphere, n-1 dimensional sphere. This is also a particularly, so this is an isometry group of Sn-1, right? So, or it is the same as the stabilizer of the Euclidean isometry group in Rn. So we have this. This is the group. Also, you can compute the dimension. You can differentiate. This is a number of equations, right? It's some amount of equations. You can actually just compute how many of them do you have. Since, well, basically you have n squared, right? You should multiply n rows by n columns, and you get totally you have n squared equations, but you can compute this by differentiating this equation. So I suggest again to differentiate in the identity matrix. Okay, let me write it di, right? And we differentiate A transpose A. And actually, also, it is an exercise. It is, you can just see it really straightforward. It is very straightforward. It will look like, from like in the beginning, it might look a little bit messy since you have just like lots of equations. But in fact, after a while, you will notice some patterns, and then you will observe that actually this gives you the matrix GA plus the matrix GA transpose, where I think of the matrix GA already as an element of the tangent space at the point I of my group G, right? And since the initial condition was this, I obtain the following condition on these matrices. And already this implies, I will write it this way. This implies that the Lie algebra of this group, I'm not right now defining, I will not define the Lie algebra for now. So I'm just writing this tangent space. It can be isomorphic. It is like isomorphic to the set of skew-symmetric matrices, right? Actually, I do not have a good notation, so I will just write it, I guess. So n, but this is skew-symmetric matrices. Another exercise, so this is exercise here, right? This is kind of part 1. And part 2, find then the dimension of ON. Yeah. But for skew-symmetric matrices, it's actually quite simple, right? Think first about the diagonal elements, and then about the off-diagonal, and you will find the dimension easily. Yeah, and here we certainly use the fact that the dimension of the manifold is the same as the dimension of the tangent space, right? So the dimensions coincide. Okay, now I wanted to mention the following theorem. So here we had this interpretation, and finally I want to say that what is known in general about homogeneous spaces. But let me just double check. I had somewhere plan, and I don't want to. Okay, I think I will mention the theorem. So there is the theorem. Let G be a. Okay, which conditions I need? Okay, let G be a Lie group. Probably sometimes it is chosen to be connected, but actually we don't need it. Let G be a Lie group. K is compact subgroup. By the way, I discussed ON and I didn't mention this very important fact. ON is a compact Lie group. Is a compact Lie group. So that's why I'm writing this in color. It is compact since it is bounded and closed in Rn squared. Since it is bounded and closed in the set of all matrices, which is just the real vector space n squared of dimension n squared. Why is it? Well, the fact that it is closed follows from being defined by the set of polynomial equations, right? The fact that it is bounded also follows from that, but a bit less, I would say explicitly. You need to observe that those conditions can be rewritten in the fact, like in the way, right? So the A transpose A in particular means that A, how should I write it? the number of squares, so that basically for any row, the number of squares, the sum of squares of elements in this row is equal to what? Is equal to 1, right? So bounded, closed, I explained. Now about bounded. And bounded follows from the fact that A transpose A equals identity, implies that A k1 squared plus and so on A kn squared. Yeah, am I correct? Yeah, I think so. Is equal to 1, right, for every k. And that's why it is bounded. Okay, so here, getting back to this, then the quotient space can be equipped with the actually unique Riemannian metric. Or maybe not unique. I guess it's not unique, actually. Anyway, let me write it this way. Then there exists a G invariant Riemannian metric on this space X, G, mod K. And in fact, our classical examples that we study will be of that type. So for example, the Euclidean space, right? The Euclidean space En, which is the Rn equipped with G, right? With the Euclidean Riemannian metric, it will look like isometry group of En over On of R. And it is known that the isometry group of the Euclidean space is decomposed into the semi-direct product of the group of parallel translations, which is going to be a normal subgroup, and the stabilizer of a point, right? So this is a group of parallel translations. And this is definitely a point of this is a group of isometries. So this is a group of parallel translations, and this is a group of isometries fixing the origin. And another example is the sphere Sn, which is also a quotient of, for example, SO n plus 1 of R over SON of R. And the isometry group is here, it will be the orientation preserving isometry group. But you can also remove S here and here, and you will get the same quotient, right? The isometry group of Sn is actually just On plus 1 of R, right? And the isometry group of Sn preserving orientation will be SON plus 1. So yeah, the idea is that usually when people work with homogeneous spaces, they usually try to avoid connected components, and then they choose G to be the connected component of the identity, and then consider the quotients by maximal compact subgroup sitting. But this theorem doesn't require you to choose actually maximal compact subgroup. And one more remark, this, as far as I remember, this condition of being compact is not, I guess, necessary. There exists Riemannian manifolds of the form G mod some subgroup H. And yeah, so there are some special cases, but the point is that if K is compact, you can always achieve, you can always equip this with the Riemannian structure. Okay, yeah, this is. There is some, unfortunately, I don't remember. There was some special example with.
Right,
Yeah, but
stabilizer.
but what if we do something with the real line, for example?
Yeah. So K is the stabilizer to a point, right? Of some fixed point. The stabilizer, if you have any Riemannian manifold whatsoever, the stabilizer of a point in the group of isometries is compact. Because it restricts to, yeah, it has a map into O of n.